Welcome to Wildcat Science with Mrs. Haugo. This is Chemistry, Chapter 2, Part 12, and we are in the third section on mixtures and gas and solutions, and we're talking about molarity. And if you recall, we had a little bit of a cliffhanger. We were in the middle of a problem. We were figuring out how much of a 1 molar ascorbic acid solution is needed if 40 thousandths of a mole of ascorbic acid is needed to completely react with the oxygen in the bag. So we plugged in our numbers. 1 molar is equal to 0.040 moles over the volume, and we solve for volume. And if you got 0.040, you got the correct answer. And it's volume, so we know the answer's gonna, or the unit's gonna be liters, but how do we get that? So let's talk about moles over molarity, which is equal to, and the unit molarity is a combined unit. It's actually moles over liters. So that is equal to moles over liters. And we know dividing by a fraction is like multiplying by its reciprocal. So that's moles times liters over moles over 1. Moles cancel, and we're left with liters. So our unit is in liters. It's really hard to like calculate out or measure out 4/100ths of a liter. It's a lot easier to do that in milliliters. So please take a minute and convert that into milliliters. So if you got 40 milliliters, that is correct. So let's check it. How much of a 1 molar ascorbic acid solution is needed? So did we answer how much? Yes, 40 milliliters. And let's look at our significant figures and see if we got it right. 1.0 has 2 sig figs, and 0.040, the first two are placeholders, so that has 2 significant digits. And ours only has 1 significant digit, so we could do one of 2 things. We could put a decimal point after that, or we could put it in scientific notation. So showing 2 significant digits, and 40 is 4.0 times 10 to the first milliliters. Okay, so we got an answer. It's in significant digits. Is it reasonable? All right, so now if I have a 1 molar solution, I'm going to have 1 mole for every liter. So if I have 0.40 moles, I should have 0.40 liters. And that is what I have. Good job. Great, so let's move from liquids and solutions to gases. Okay, our last concept of this whole chapter is going to be mixtures of gases. So many mixtures are gases. And some things to remember or know about gases are gases expand to fill their container. So if I were to release some gas here, like some carbon dioxide or nitrogen or whatever, it would fill up the entire room. Let's take a look on page 62. Okay, so looking at our book, if we have air, which is a mixture of gases, it's mostly going to be nitrogen. We've got about 20% oxygen, and then about 1% argon and water vapor and a little bit of carbon dioxide. We know if that little bit goes up or down, that can cause some problems, and a bunch of trace gases. And we know that air or any gas will expand to fill its container. So if I have 1 gram of air and it has a little container, a milliliter, it'll expand to fill that. If I give it a liter, it'll expand to fill that. And if I give it a cubic meter, which is like roughly 3 feet by 3 feet by 3 feet, it'll expand to fill that. The thing that would be different would be the pressure. If that 1 gram of air is in a very small area, it will have a very high pressure. If it is in, if you have 1 gram of air in 1 liter, it'll have 1 atm or 1 atmosphere of pressure. That's the pressure at sea level, so just normal air pressure. And then if I have a little bit of air in a big space, the pressure will be very low, 0.001 atms, 1,000th of the pressure at atmosphere. You wouldn't want to be in that bubble because your lungs wouldn't work there. Looking over here, we have 1 mole of all of our gases. And the 3 examples are oxygen, nitrogen, and carbon dioxide at STP, which is standard temperature pressure. So the standard temperature is 0 degrees Celsius, and standard pressure is 1 atm, 1 atmosphere. They will all take up the same amount of volume if you have 1 mole. It doesn't matter which gas it is, it will take up the same volume, 22.4 liters. As we were talking about, the density of the gas depends on the temperature and the pressure. Please write that down. In the small box, the pressure was really high, so that was a very dense gas. And in the big box, the pressure was very low, and so the density was very low. And then if you noticed in the book that the temperature was held constant, but that would also affect density of gas. So we always need to be talking about standards. We always need to clarify what temperature and what pressure we're dealing with when we're dealing with a gas, because it changes everything. So please write down the standards. 1 mole of any gas at standard temperature pressure, which we abbreviate STP, is 0 degrees Celsius and 1 atm. And the volume of any mole of gas at that pressure and temperature will be 22.4 liters. Doesn't matter which gas it is. So you don't have to write this down, but let's talk about Dalton's law of partial pressure, because that is an important one. So if you recall, looking in our book, Dalton's law of partial pressure says the total pressure is the sum of the partial pressures of each individual gas in the mixture. So if we have 3 different gases, the pressure of gas 1 plus the pressure of gas 2 plus the pressure of gas 3 would add up to the total pressure. So that's pretty common sense. Let's look at an example. If I have 1 liter of helium and neon, 75% helium, 25% neon, and it's at standard temperature pressure, what is the partial pressure of the helium alone? So at STP, standard temperature pressure, that would be 1 atm or 101,325 pascals. And so we know that the pressure of the helium plus the pressure of the neon is going to equal that total pressure. So then the pressure of the helium is just going to be 75% of that. So 75% of 101,325 pascals is 75,994 pascals. Let's look at a picture that illustrates this. So in air, we have 78% nitrogen, 20% oxygen, and about 1% argon. So since they have different amounts they have different percentages and different amounts, they're going to have different masses. So we can't have equal pressure and equal volume because we have different masses of each of those 3 different gases found in air. So nitrogen makes up 78% of the air, and then if I have it at 1 atmosphere, like if I have 1 liter of air at 1 atmosphere, if you just take out the nitrogen, it would take up 0.78 liters of volume. And then the oxygen would take up 0.21 liters of volume, and then the argon would take up about 0.01 liters of volume. What happens if I flipped it? Oops. If I said, well, I want them to all take up the same volume, well then they can't have the same pressure. So one or the other has to change. So if I have 0.78, if 78% of that mixture is nitrogen, and I give it a liter, it's going to have less pressure than all of the air in a liter. So it'll be less than 1 atm, it'll be 0.78 atm. And that oxygen, if that oxygen expands to fill that whole liter. There's less of it, so it's going to have less pressure, 0.21. And then if you give that little bit of argon a whole liter to expand, it will have very low pressure, 0.01 atm roughly. The last thing we are going to talk about is magical chemical reactions found on page 64 and 65. And they're talking about the chemical reaction of sodium with chlorine to produce sodium chloride. And we're going to have a class discussion about that, and I would like you to be able to tell me the properties of sodium, the properties of chlorine, and the properties of sodium chloride. So please write the black stuff down in your notes, and let's just quick look at this. So we have sodium metals, very reactive, found in oil. We've got table salt, sodium chloride, and then we have our sodium and our chlorine combining to make sodium chloride, which we know salts are an important part of all animals' diets. So, congratulations on finishing Chapter 2 notes. Good job.